What is an exponential? We're going to start by looking at this table of values where we have y equals 2x, y equals 2x squared, y equals 2x to the third, y equals 2 to the x. When we evaluate, we're plugging 1 in for the x. 2 times 1 is 2. 2 times x squared, 1 squared is 1 times 2 is 2. We're plugging 1 in again. 1 cubed is 1. 1 times 2 is 2. And then 2 to the first power is 2. So when x is 1, we get the same value for all four expressions. We get the value 2. This time when we're plugging in 10, 2 times 10 is 20. 10 squared is 100, and 2 times that would be 200. 10 cubed would be 1,000, and 2 times 1,000 would be 2,000. But 2 to the 10th power would be 1,024. Then we're going to use x as 20. So 2 times 20 is 40. When we plug 20 in here, 20 squared, 400 times 2 would be 800. 20 cubed times 2 is going to give us 16,000. And then when we put 20 in for the exponent here, we're going to get 1,048,576. So at that component, you'll see we get quite a bit of a difference. So from the table of values, you'll see that at first, with smaller values, this exponent is relatively the same and starts off kind of slow. But as we get to bigger values, there is a significant difference in the amount that you will gain. And that is the characteristic of exponential functions. So we have the base equation, y equals a times b to the x. As we talk about this a value is considered the initial value of the function. The b value is considered the base of that exponential function. This b value cannot equal 1, but it has to also be greater than 0. Then as we look at the graph of an exponential function, I'm not going to look at specifics of the graph, but just the basic shape of that graph. It will look something like this, where it starts off very slow, very close to the x-axis, but then it gradually increases and then shoots up significantly. So it does grow. So we call this graph a growth, an exponential growth. Some exponential graphs will look like this, where it's going in the other direction, and we call this an exponential decay graph. And we will talk about the difference in those two types of graphs. What has to happen before you get a growth versus a decay graph. In either of these graphs, we'll talk about the domain. The domain for either of these graphs will be all real numbers. The range for these graphs, you can see, is all above 0. So the range would be y is greater than 0. Now let's just refresh our memory a little bit. If we were writing this in interval notation, that would be negative infinity to positive infinity. The range here would be from 0 to positive infinity. It is not equal to 0. Notice it gets very close to the x-axis but does not touch the x-axis. Excuse me. So, as we continue to look at the differences here, the reason that we have a growth is that when that base value is greater than 1, anytime the base value is greater than 1, we will have growth in our function. Anytime the base value is between 0 and 1, we will have the decay value. So an example of this would be y equals 3 to the x power. That base is bigger than 1, so it would represent a growth exponential. An example here of a decay would be y equals 2/3 to the x power. That value of the base is between 0 and 1, so that's why it represents a decay exponential function. There are other ways that we also can get a decay function through transformations, but we're not going to talk about that right now. We will talk about that more when we get into the transformations. For now, let's talk about how we can look at an exponential equation and determine if it is a growth or decay. So let's look at a few examples. We have y equals 1/2 times 1.2 to the x power. We have y equals 100 times 1/3 to the x power. And we have y equals 5 times 7/4 to the x power. And what I want you to think is which of these would represent a growth exponential function and which of these would represent a decay exponential function. What do we have to look at to determine whether it is growth or decay? We're looking at this base value. The a value, which is the initial value, makes no determination in whether it's growth or decay. So that being a fraction does not matter. What we're looking at is the b value. This value is bigger than 1, so this would represent a growth exponential function. When we look at this second example, the a value is 100. The initial value is 100, but the b value, the base value, is between 0 and 1, and so that makes it a decay exponential function. When we look at the third example, the a value is 5. Again, that initial value, it does not affect whether it's growth or decay, but we're looking at the base value. Now it is in fraction form. That doesn't matter. That fraction, 7/4, is still bigger than 1, so it is still a growth exponential function, even though it is in fraction form. Don't let the fraction form sway you from determining whether it's growth or decay. Just because it's a fraction doesn't mean it's not greater than 1. The second thing that we want to look at is, can you just determine, is it an exponential equation? So let's look at some examples here. Y equals 5x to the 10th power. Y equals 0 to the x power. Y equals 2 times 0.5 to the x power. Are these exponential equations? We want to decide, are these exponential functions? When we look at this particular problem, the x is a base. So if the x is the base, this is not an exponential function. When we look at this particular problem, the x is in the exponent, but look at the value of that base. That base is 0. It does not fit the criteria because it has to be greater than 0. So this is not an exponential function. When we look at the third example, we have an initial value of 2, we have a base of 0.5, and the x is in the exponent, so it does meet the criteria of being an exponential function. So it is an exponential function. So our first video is going over the basics of what does it take to be an exponential function. We looked at how it relates to power functions and linear functions, how although they increase, an exponential function will show greater increase in the long run, an increase at a greater rate. We look at the basic equation, y equals a to the times b to the x power, a being the initial value, b being the base. There are some restrictions on the base. The base cannot equal 1 and the base is greater than 0. So we know our basic graph will be above the x-axis. When we look at the domain and the range, the domain is all real numbers, the range is greater than 0. We looked at ways to look at the equation and decide whether it's a growth or decay equation. We look at the graph and can decide growth or decay. We also looked at looking at the equation. Is it an exponential function or not?